everybody, and thank you to be here at Daho.am 2018. Considering the tough schedule that we are going to have today, I would love to introduce you our first speaker, Professor Daniel Cremers. He founded several companies, but he is today here to introduce you to one of his, let's say, pearl one. And he's going to speak about Artisans Corporation and how they are going to change the autonomous driving industry. So please welcome to the stage to Professor Daniel Cremer.
Okay, I hope you can hear me. Welcome everyone to my presentation. My name is indeed Daniel Cremers. I'm a professor at TU Munich in computer science and mathematics and co-founder of Artisans Corporation. So before I get into Artisans, let me tell you a little bit about my background. I'm at TU Munich, as I said. I'm heading the chair of computer vision and artificial intelligence. I've been a professor there for about 10 years now, and I've built up one of the largest academic research labs in this area of computer vision. So we currently have, you see it here, about 20 PhD students and a number of postdoctoral researchers working on quite a diverse range of topics. We're quite big in the field of computer vision, among other things. This year we're actually organizing one of the 3 big computer vision conferences, the European Conference on Computer Vision, and it's going to take place in September 2018, so later this year, in just a few months. And we're expecting for this conference about 3,000 participants, so it's going to be like this, but bigger. So if you like Munich, and if this is maybe your first visit to Munich, consider coming again, maybe for this event. And this might be exciting if you get excited about computer vision. This may be an opportunity to show you the latest state-of-the-art research in that field. Our team has been working on a diverse range of topics. It's a little bit hard to summarize all the things we've done. I've tried to group them, but with about 30 people working independently on 30 different things at any given time, it's hard to keep actually track of what everyone is doing. So here's a few glimpses into some of the things we do. We work on autonomous robots, for example, driving, but also flying robots. Here you see a system that flies in the air. You've seen quadricopters many times, I'm sure. The difference is that these are not human piloted. They are controlled by a machine. So the machine uses the onboard sensors, in particular the camera, to determine where the drone is and where it should be. And then you can do all sorts of things. For example, you can do gesture control of little so-called nanocopters. These are quadricopters that fit in the palm of your hand. Here you see one, and on the bottom right you see the video footage recorded from the nanocopter. So you can use it to do selfies, for example. Obviously, the first thing every sane person tends to do nowadays. But you can think of other applications, video conferencing, and you name it. So there's a lot of potential applications for the technologies we've been developing. The topic that I'm focused on a lot is that of camera-based reconstruction. Here you see one of many examples from our research, the work that we did about 3-4 years ago, actually. We can record videos from 16 synchronized cameras. You see the cameras shown there. And we can actually recover the action in 3D. At a resolution in space and time that is very high, you can see we can reconstruct the entire rope of a rope jumping dog just from camera images. But we can do more. This leads to what's often called 3D television, because you can back project the colors and then you can actually synthesize what would the action have looked like if I had a camera in this location. So like the point where we're looking at the action now, there is never been a camera, but we can simulate what would have been the view from this vantage point. And this leads to what's called free viewpoint television. But beyond 3D television, we can also do 3D photography. We can get a simple off-the-shelf commercial depth sensing camera. You see it on the left here. We just place it on the table, and then we can take a person, rotate the person around just once, and we have a complete colored 3D model coming up. So you see in the back, the model is already generated by the time you finish the term. And we can just, send that as it is to a 3D printer and get lots of miniature copies of people. It's like, like a photo book, but tangible 3D. So you can basically scan your friends, your family, your children, for the grandparents who actually have a tangible memory of their children. We recently sent that to a full-body scanner. This is our president of TU Munich, Hermann, and I didn't want to, turn him on a chair like I feel a little bit awkward there. And so we created a full-body scanner that doesn't require the person to move around. And then we can get complete full-body scans printed out. And he was definitely happy. He told me that he put them on the piano at his home. And so these days we get a lot of requests. Everyone wants to get scanned. We actually did create a startup company out of this, but it wasn't too successful. So if you have ideas on how to make this into a big business, I'd be very open to this. The startup I wanted to talk to you about today is a startup that I created with my two co-founders, Andre and Till. It's a startup that we call Artisense, for artificial intelligence sensing. It's a VC-backed startup. We raised several million seed funding earlier this year. We have offices in Munich, in Palo Alto, and in Tokyo. And the key focus is to develop technologies for autonomous systems. For example, self-driving cars, drones, robots, you name it. And the key focus, I'll show you some of the results we've obtained in the startup, some of the technologies we've developed, and we're currently commercializing. And we are actually right now in the process of putting these technologies literally on the road, collecting data and generating 3D scans of the world. Here's the first result that is part of the intellectual property of Artisense. It's a technique that we call direct sparse odometry. It uses just one single standard gray value camera, much like the ones you have on your cell phone, and you can see we can track that camera over very large distances. Here we go through an entire subway station, and you see in the process, in real time, the whole world in front of the camera is being reconstructed on the fly. And this, even though there's very little texture, often very gray streets, often very drastic changes in brightness. And the way we do this is we track the camera frame by frame. How does it rotate? How does it move at any given frame? And of course, when you do that in a computer, you make errors invariably. And these errors, they will accumulate. So over thousands of frames, these errors will add up to what is called a drift. And you see the drift here. The bicycle seen on the top left in the image is reconstructed twice here, right? And there is an offset of maybe 2 or 3 meters, but on a distance of hundreds of meters, which means the precision of this algorithm, it's called SLAM, for Simultaneous Localization and Mapping. The precision of this SLAM algorithm is less than 1%. It's, in fact, we evaluated on many, many sequences. It is by far the world's most accurate, real-time capable SLAM system. Here's the evaluations. We compared to the state-of-the-art, a technique called ORB-SLAM that was generated by a team in Zaragoza, quite an amazing algorithm. But you can see what we plot here is the error in translation, in rotation, and scale. And the number of runs that we can do with that error. And ideally, you want to be on the top left in these plots, meaning smaller errors, more sequences you can track. So for example, if you say, what is the error on the best 300 out of 500 sequences? ORB-SLAM has an error of 6. We have an error of 1, meaning the error is reduced by a factor of 6, almost an order of magnitude better than the state-of-the-art. Or if you say you want a maximum error of 2, how many sequences out of the 500 can you track with that error? ORB-SLAM can track 100, we can track 400 with the same precision. Meaning we are 4 times more robust than ORB-SLAM if you want to measure it in this way. And so these technologies, we've extended them. This is just a monocular version, meaning it uses just one camera to recover the world. You can extend this to 2 cameras. This is something we showed last year. And what you see here are reconstructions generated out of a driving car. Again, on the bottom left, on the bottom you see the 2 images from the car. So this is just a standard stereo camera rig in a car. And on the top you see the reconstructions and the camera trajectory, the car's trajectory that we can compute in real time. And you see there's almost no drift here. Once we drive around the block, things actually do line up almost perfectly. And so you can keep driving and create in real time, out of a driving car, very large-scale, high-resolution 3D maps of the world around you. And now imagine if you were to put this technology into every car that's driving out there, and then fuse all the data in a cloud, that's what we're working on, then you can instantly map all of Germany or Europe in no time. Now, you've probably heard about self-driving cars. It's been in the media quite a lot. People talk about self-driving cars, about driver assistance, etc. I have worked with car companies for about 15 years now, with Daimler, with BMW, with Audi, with many, many companies. And I can tell you, even among the experts, there is no consensus of what are really the core technologies of the future self-driving car. Is it going to have LiDAR? Is it going to have cameras? Which sensors will it rely on? Which algorithms will it require to run autonomously, to drive autonomously? There is no consensus. And I'm not here to tell you what the future self-driving car will contain, but I can guarantee you it will contain technologies like this one. Technologies that can leverage camera data to reconstruct the world in real time at high precision, on a simple laptop CPU. So you don't even need a GPU, NVIDIA board, whatever, to do this. This takes just one small, even on a smartphone you could run this. And we can do more. We can do semantic slam. What you see here are results, 3D reconstruction, with semantic labeling of all the points. The different colors tell you what is street, what is sidewalk, what are cars, what are pedestrians, what are houses, what are trees, you name it. Here's another example. And this is vital because you want to determine obstacles, but you also want to see what is the obstacle that I'm looking at. Is it, say, if something is in your driving corridor, is it a person, is it a trash can, what is it? Because you need to know. At some point, it's going to be important, not just to determine obstacles, but to actually identify what kind of obstacle are we looking at here. And we can do more. We can enhance camera-based SLAM with inertial sensors. Inertial sensors are what is in the human brain called the vestibular system. It tells you about your rotation, about your accelerations. We can bring that into visual SLAM and drastically boost the precision, make it more robust to very drastic rotations, to very blurry imagery, because we have an additional sensor that gives us complementary redundancy information that makes everything more stable. Here you see very fast rotations, and still we can very reliably track the camera over very, very long distances. But we can do more. I'm sure you've heard about one of the biggest hypes in computer vision ever. The biggest one I've ever witnessed is that of deep learning, deep neural networks. And I must admit, there is a belief in the community now that everything can be done with a deep network. You just take your task, you take enough training data, you train some random network, and out comes a perfectly acting system. There are companies who will make you believe that you can do a self-driving car with an end-to-end trained neural network. In goes the sensor data, out comes the driving car. Honestly, I don't think that's going to work. I think we're exaggerating a little bit with our expectations here. Deep neural networks do amazing things, but they cannot solve every problem. And one of the challenges is how to bring deep networks into the game for 3D reconstruction and SLAM. One of the amazing things you can do with deep networks is you can take one single image and predict what is the depth. This is what you see here. And you see, The state-of-the-art networks are doing so-so. You can recognize there is a certain depth, you can see cars, but it's not, it's very blurry. We actually leveraged on this, we expanded this and showed that you can do much better. You can devise more sophisticated network architectures that give you much more precision in terms of the depths that they predict. And so you can now start from that, use that depths and bring it into SLAM algorithms. And this is what we call deep virtual stereo. Basically, we take an input image, just one single camera, not two cameras, one only, and we basically predict, loosely speaking, what would the second camera see if there was a second camera. And then we can run a stereo method, assuming there's two cameras, but it only uses one of the two cameras, and it essentially hallucinates the second camera with a deep network. And so we can map at large scale, at high resolution, from just one single moving camera, the world around us. And there's obviously a huge benefit if you can reduce the number of cameras and still get a similar performance. Of course, you don't want to lose performance. You want to preserve the same performance, maybe even better. And so we looked at evaluations and we found this is the ground truth on the top. This is what the car actually drove. On the left is what you get with just one camera. It doesn't work, so it recovers the trajectory, but every now and then it doesn't estimate the scale of the world properly. Because once you have a single moving camera, you cannot get the scale of the world. You can get it once you add a second camera, that's what you see in the middle. And what we showed this year is you can also get the scale once you add a neural network. Why? Because the network knows what the world looks like. It can see, it can learn from examples, what do cars typically look like, what is their typical size, etc. And then you get something that is on par with the stereo method, except it only uses one camera, not two. Here's more examples. Again, you see the stereo version and the monocular with deep learning, they work almost on par. And so the question is, how accurate is this technique? So we evaluated again on many, many sequences, and what we found is on the left you see the evaluations, the performance numbers of the three state-of-the-art stereo methods. Stereo LSD SLAM is a technique we developed before. Orb SLAM is the competitors in Zaragoza. Stereo DSO here. These are all methods that use two cameras. Here comes the deep learning enhanced method that only needs one camera. And you see the solid numbers are the best performing methods. You see this method is actually on par, on average actually outperforms the stereo methods, even though it only leverages one single camera. So to summarize, I talked about 3D reconstruction for images, how you can recover actions in time from synchronized cameras, how you can do 3D photography, how you can even do full body 3D scanning, and then I introduced to you our new startup Artisans, with the focus on technologies for autonomous systems, in particular 3D reconstruction technologies using cameras in particular to recover the world at high precision and high resolution and large scale in real time. Thank you very much for your attention.
Thank you very much, Professor. I would love you to ask questions, and feel free to stand up in front of the stage. There's a mic in the middle, and you can ask all questions to the stage that also everyone can understand. Okay, I will bring you this one that's faster.
So thank you for the great talk. I was wondering for your direct sparse odometry, the sceneries were more static. How do you deal with dynamic objects?
This is a good question. The question is, for those who didn't hear it, how we deal with moving objects. So all of these SLAM algorithms are based on the assumption that the only thing that moves is your camera, and the assumption that the world actually does not move from one frame to the next. This is a very naive assumption. Especially in traffic, we can have lots of moving objects. In practice, these methods are extremely robust to moving objects. Like in the subway example, there are people walking through the camera, etc. basically it ignores moving objects. The next better solution would be to actually model the moving objects. This is what leads to what's called dynamic SLAM, and this is things that we're developing right now. I think there was another question. Yes?
Is your project related to the project that TomTom and NVIDIA are doing for the high resolution maps?
Yes. So there are many companies, of course, who work on these things. TomTom is one of them. TomTom recently acquired a startup that is based in Berlin, and I know are using DSO. I'm not sure if they have license, actually. So there is a lot of competing companies out there that are building on similar ideas. I think the key difference is that we are actually developers of these leading technologies, and as I pointed out, these are by far the world's most accurate SLAM technologies.
Hi. You said like with visual inertial you have just one camera and with stereo you have two, and they compare in accuracy, right? So what would happen if you add a second camera to the visual inertial? Does it exceed the stereo accuracy?
Yes.
Okay.
So we have shown if you add stereo and inertial, you get even better precision. So basically, with more sensors, you get better robustness, better precision, and so there is a consensus that sensor fusion is what you should be doing. I should say that depends on how you do it. If you don't know what you're doing, you should not fuse sensors. The issue is if you fuse different sensors and you don't know what you're doing, just naively fuse the output, then you are dominated by the worst of the sensors. Whereas you want to do the fusion in a way that the best of the sensors dominates the performance. And this is rather tricky to make it happen. Yes.
I have a question. What is your roadmap when you want to release this stuff like a product version?
So there's a long answer and a short answer to what is our roadmap. The short answer is there are two business cases that we focus on these days. One is we can license our sensor technology, either just the algorithms or the algorithms combined with stereo inertial sensor. So we have a prototype that we can demo and that we can mass produce. The second business case is the recording of 3D data, point clouds, because I think there's great value in data, in particular in 3D data. It's very easy to record data, just putting cameras into cars and driving around, but our technologies enable us to actually create 3D data of the world.
Can you give us a rough estimation date, in what horizon we can expect this as a product form?
So we're aiming at having products on the road next year. The idea is that we're not actually putting a self-driving car on the road next year. I think that's a little bit premature, although companies are doing that as we speak. But we will provide the technologies that you need to develop and build self-driving cars. And I think this will be one of the core technologies: SLAM, dynamic SLAM, semantic SLAM, all of these.
What would you say the best solution for different weather conditions is?
Can you speak up a little bit?
What would be the solution for different weather conditions like snow, rain, stuff like that? Is it different sensors or some deep learning network?
Yes, you basically gave the answer. One of the challenges that we're working on now is how to generalize this to varying weather conditions. Let's say you drive around the block and you want to relocalize yourself, but maybe it's not the same time of day, maybe it's not the same weather, then the world looks very different. And the question is, how can we robustly perform in very changing lighting and weather conditions and daylight and night conditions? And indeed, the two techniques we leverage on is deep learning and sensor fusion.
how are you dealing with data privacy issues? For example, are you dealing with neural networks also to recognize this person, or it's something what is relevant?
So this is a good question. How we deal with data privacy is a very important question. In particular, these days it's becoming increasingly a valid concern in the public. We don't actually do face recognition because for what we do it's not important to recognize. It's important to know this is a person, but what person doesn't actually matter.
Yeah, sure. Maybe you also mentioned that you're evaluating to maybe put the data for sharing purposes for companies. So, for example, if you're walking by or passing by, for example, a license plate is also relevant.
Yes. So the two things that we focus on these days in terms of privacy is removing faces and removing license plates. But the good news is this can be done fairly automatically these days. There are algorithms that can reliably detect license plates, reliably detect faces, and then we can automatically remove it.
Automatically during generation of the data.
Yeah.
Okay.
How do you track the position of the camera?
How do we track the position of the camera? Well, this would be another hour of presentation. It's all detailed in a variety of publications, so we do publish a lot of the technologies we develop. It's not that you can reproduce it from the paper or re-implement it by reading the paper. There's a lot of additional expertise to actually make things work, but the key ideas are actually published. And so, but it takes a bit of expertise, a bit of mathematical background, and I think for this larger audience, this would go a little bit beyond the scope of this conference.
You also mentioned the generation of 3D models and point clouds. There are a number of commercially available solutions for this, for photogrammetry. And as far as I know them, they need a lot of pictures, they need a lot of very good image quality, high resolution, and they're very slow. So is your solution a lot faster and a lot less sensitive?
Yes, it is much faster and much more robust. So as I said, in terms of robustness and precision, it is by far the most accurate and most robust real-time capable slider. If you don't care about real-time, as you say, there are algorithms that can take days to reconstruct things, but for self-driving cars, I think there is a need for real-time performance. For example, the rope jumping girl, I didn't tell you, but it takes 3 minutes per frame of the video to reconstruct each girl, right? And 3 minutes is fairly fast, I find. This was the fastest we could do with GPU support and everything, but it's far from real time. And if you take 3 minutes to reconstruct a rope jumping girl in front of a car, by the time you have it reconstructed, the girl is dead, right? So, we need real time.
You mentioned the virtual stereo part. Isn't there an idea to use additional network support for actual stereo as well to improve it even further?
Yes. Yes, it's a bit related to the question someone was asking. Ideally, you leverage all the sensor data you have. What the last work shows is we can also leverage on examples on training data to boost the performance of these methods. And show that, for example, in some applications, customers don't want 2 cameras. They say, can you do the same with 1 camera? And we show that, yes, you can do it. But indeed, if you were to use 2 cameras, inertial sensor and deep learning, you would indeed get the best performance.
Have you also tried to use a reference model so that you create, let's say, based on crowdsourcing data, you create a reference model, and now you have that. And as you sense data, you could maybe even faster figure out where the car is.
Yes. So there is a lot of model-based reconstruction algorithms out there. We've also developed model-based reconstruction methods. The problem is it's limited to a specific type of objects. For example, you can have models of cars, and then that can improve the car reconstruction. But if you have a dog or something running through the scene, it's not so easy to have model-based reconstructions of dogs because they articulate in rather various ways, and that makes it much more complicated. So model-based reconstruction can be done, but if the model space grows very high-dimensional and very non-rigid, etc., then things get very complicated. But we work on model-based reconstruction, and there is definitely a use case for that, yes.
So if we don't have any question, I would love to ask you another big applause for Professor Cremer. Thank you very much for being with us.